Right. Now we're going to look at anti-differentiating involving partial fractions. So first of all, to have a look at the technique, it's going to look something like this. And you're going to say to yourself, well, how do I know I need to use partial fractions? First of all, if we look at this function, it's a fraction. So we've dealt with fractions before and we've thought about it as tan. Tan normally is a constant over a squared plus x squared, so it doesn't suit that. There's no powers, it's not change of variable, it's not linear substitution, it doesn't look like any of the trig things. We don't really have any options left. So the last technique is what they call resolving into partial fractions. Because we can see the denominator's got an x plus 1 and an x minus 3, we can then say that we would have had two fractions that got added together in the first place. Now we're not anti-differentiating yet, we're resolving into partial fractions. So there would have been something over the first fraction and something over the second fraction, and that together when added would have produced a function that looks like this. So, using lowest common denominator, this must be x plus 1 and x minus 3 as my partial fractions, and this would be a times x minus 3 and b times x plus 1. Effectively, you imagine it's like cross multiplying. Okay? So, if these two fractions are equal, that means that 2x plus 1, which was my numerator, had to equal a x minus 3 and b x plus 1, which is your numerator. Now you could expand and equate coefficients and all this sort of stuff, but I normally try and select two values that will make life easy for me. So I'm going to substitute x equals 3 into both sides. So we're going to get 2 lots of 3 plus 1 equals a outside of 3 minus 3 plus b outside of 3 plus 1. So we get 7 equals 4b, and therefore b is 7 over 4. Alright, so the reason we chose 3 is to make this become 0. Next value I'm going to choose is x equals negative 1. So by substitution you get 2 lots of negative 1 plus 1 equals a outside of negative 1 minus 3 plus b outside of negative 1 plus 1. Reason for negative 1 is to make this bracket disappear. Therefore negative 2 plus 1, you get negative 1 equals negative 4a, so a is a quarter. So that means that the integral of 2x plus 1 over x plus 1 x minus 3 can actually be written as the integral of a quarter over x plus 1 and 7 on 4 over x minus 3. So what that's done, we haven't done any anti-differentiation, any calculus yet. What we've done is a bit of algebra and resolved and turned a fraction, complex fraction, into the sum of two simple fractions. What that allows me to do now is anti-differentiate. Right? So a quarter over x plus 1, quarter's a constant, and you're left with log x plus 1. And 7 on 4 is a constant, and log x minus 3. This comes from the fact, we did it earlier, that f dash x over fx is equal to log f of x. Right, there's the rule that we're dealing with. Okay, so you'll find that partial fractions often end up being logs when you anti-differentiate. Let's try one more. we've got 3x plus 5, well, one more of this form anyway, over x squared minus 5x minus 24 dx. Okay, we're going to look and see, first of all, not a tan. Could it be a straight out log? Probably not. Now this is important for you to check just to make life easy for yourself. Sometimes it could be, but if we looked at the bottom line here, the derivative of that would be 2x minus 5. My top line is 3x plus 5. So they're not the same. So therefore it can't be a straight out log from the beginning. So we're going to break this up into partial fractions. First of all, we need to say that 3x plus 5 over x squared minus 5x minus 24 can actually be written as 3x plus 5 over, and what we're looking for here is to factorise that. So you've got factors of 24, which is 8 and 3. We need to end up with a negative 5, so it's minus 5 plus 3. So that and that are the same thing. Okay? We'll go into partial fractions. So we would have had two simple fractions, a over x minus 8 and b over x plus 3. They're the two fractions that together would have added up to produce 3x plus 5 over the composite. Therefore, by lowest common denominator, so we'll get 3x plus 5, which is the numerator here, has to equal a x plus 3 and b x minus 8. Okay, so that was cross multiplying there to come up with that as our numerator. Picking values. Right, we're going to sub in x equals negative 3, so you get negative 9 plus 5, you get negative 4 equals, this first bracket will become 0. What are we substituting? Negative 3 minus 8, so you get minus 11b. So b is 4 over 11. Then we will substitute 8, and we'll substitute 8 to make this bracket equal 0. So if we substitute 8, 3 8's 24 and 5, 29. If you put 8 in here, you get 11a. So a is 29 on 11. So our actual integral will become 29 over 11 over x minus 8 and 4 over 11 over x plus 3 dx. Okay. And as we've said before, let's go with logs. 29 over 11 log of x minus 8 and 4 over 11 log of x plus 3 plus my constant. So, one more type of function we have to deal with is something that looks like in the form of, say, 2x minus 3 over x plus 1 all squared dx. Right. Now we need to break this into two functions. Well, we don't actually have to do partial fractions, but I'll show you how to do this using partial fractions, and then I'll show you the other technique. We have to work out what the two fractions were. So a lot of people just assume you'd have x plus 1 on the bottom, which is correct. So you say have a over x plus 1. Then we have to work out what the other function was. Now it can't be x plus 1 by itself, because that would just give me a denominator of x plus 1. So what you need to have is x plus 1 all squared. And then you have another constant on top, say b. Okay, so it's important with a repeated factor, and this is what this is called. It's a repeated factor. So because you've got like x plus 1 squared or anything just squared on the bottom, you need to split it into two fractions, the singular fraction and then the squared fraction. Okay, so once we've done that, we do our lowest common denominator type thing again. So 2x minus 3, which is our numerator here, has to equal a. Now, the denominator here is x plus 1, we want it to be x plus 1 squared, so we're missing a factor of x plus 1. And then over here, we've got b sitting on x plus 1 all squared. The denominator is perfect, so we don't have to touch the bottom line. Top line, so we have it left as b. We're going to do the same technique we did previously, so we're going to substitute appropriate values. The first value I would substitute is -1, because that would mean that this bracket will disappear. So if we substitute -1, we get -2, take away 3 is -5. Put -1 in here, you get 0, and you're left with b just equaling -5. Now, there's nothing left to substitute. There's no obvious value, so the next simplest thing always is just substitute 0. If I put 0 on both sides, I get -3 equals a, because you get 0 plus 1, plus b. Therefore, -3 equals a minus 5, because b is minus 5. So that leaves me with a equaling 2. Therefore, that integral, 2x minus 3 on x plus 1 squared, is actually the same as evaluating the integral of 2 over x plus 1 minus 5 over x plus 1 all squared dx. So, antiderivative of 2 over x plus 1 is 2 log of x plus 1. And now when we want to antidifferentiate 5 over x plus 1 all squared, right, I'm going to take an extra line here. That's like doing 5 integral x plus 1 to the power of -2. Right, it's not going to be a log because you've got a squared on the bottom. And so if we turn around and add 1 to the power, that becomes -1. And you divide by the power, it's -1. You divide by the derivative of the inside function, which is 1. Okay? So in other words, the answer is now 2 log x plus 1, and the negative over negative plus 5 over x plus 1 plus c. So the power -1 took me back down to the bottom line. X plus 1, the negative divided by the negative is positive, and there you have it. You'll find that this, when you've got a repeated factor, is quite common to have an answer that one component is log and the other component is a fraction based on the single function.